Hi, welcome to the channel. Today let's try solving the lead code 22 generate parentheses. So given n pairs of parentheses, write a function to generate all the combinations of well-formed parentheses. So we have n equals to 3, which means 3 pairs, and we have to return all the possible well-formed parentheses strings. To solve this problem, uh, so let's say the given input is 3 and the output required is the given list. Okay, so this is the desired output which we are aiming for. So now let's see if we can solve this problem. uh, let's see if we have a subproblem structure to this one. Like, can we somehow solve a bunch of small subproblems and somehow get the solution for the overall problem? So let's see if we can find a solution, uh, aiming to have a subproblem substructure, right? So for example, so here we have n equals to 3, and the length of each valid parenthesis is, if you say, it's 6, right? So each valid parenthesis length is 6. Now let's take a scenario where I just let's see. So our goal is to see if there is a subproblem structure to this one. So for that, I just drew some 6 empty blanks. Now assume that let's see, we're just trying to fill this particular blank here, which is at index 0. So we have two choices, right? So we have is just an open bracket and a closed bracket. So any blank will only have one of these two, right? So let's see, for the first blank, uh, what are the possible choices that this blank can have? So this can only have an open bracket, and this one. So let's assume that whatever we just filled is a subproblem, and assume that this whole subproblem is, so I'm not responsible for solving this subproblem. Like, my colleague or a friend is responsible for solving the other. He's just for filling the other 5 slots. So I just give him, like, let's say if I just give him uh, a partial solution which I created, and also the subproblem definition to him. So what are the, so now let's assume I am my colleague, and here now I'll have two choices, like an open or close. Now I do the same thing. So I pass on the rest of the subproblem to my friend or a colleague, and he's responsible for filling this one. So here again, he has two choices to fill, to open and a close one. Okay. Now let's see. Now it's clear that it's possible to create a solution by solving subproblems, but let's be even more clear by drawing a recursion tree, if that helps. Sorry. Okay, so let's say if this is the root node, and this root node has made a choice by filling 3 4 5, by filling this open. And no, okay, so the subproblem, the definition that is being passed is from, now this node, let's say this is 0 node and this is 1 node. Now this is responsible for solving the rest of, or for filling the rest of the 5 slots. Now he has, now this particular node, sorry, has two choices, right? So this is 0 and this is so okay, so this is already filled. So this one is filled by the guy above, and now he's responsible for these from 1 to 5. Now if you see, second slot or the index 1 element has two choices, right? So it can be an open or a closed one. So you have two choices. So he will make both the choices. Let's say you have open here and close here, and the rest of the four slots will be filled by the next set of colleagues or friends. And why do we have only one choice for this guy? It's because, we need the parenthesis to be a valid one. So a valid one cannot have a closed one at the beginning. It should have an open one. So in the same way, they'll have two choices. They make those. This one will have two choices. They make those. And at the end, that is the leaf nodes, will have the final result. And they maybe append it to a global result or somehow. So if you see here, this is a combinatorial problem. Now assume uh, if there is no valid parenthesis condition, right? Assume if there is no valid parenthesis condition. Now then it would be straightforward. You have 6 slots. You have 6 slots. I mean, here n is equals to 3, which is why we have 6 slots. If it is 4, then it would be 8. So let's say if there is no valid parenthesis condition, then it would be straightforward. So uh, each slot will have two choices, like either open or close, open or close. So we'll have two choices at each slot. So it would be 2 power n, right? Okay, so we have n is equals to 3 here. So the given input is in terms of pairs, right? So it would be, so this length is 2n, right? So it would be 2 power 2n, that is equals to 4 power n, because if you, it's like 2 square of n, so which is equals to 4 power n. So this 4 power n is the maximum the size or the output size, you can say, output size of the given problem, if there is if this condition is not present. Like if there is no valid parenthesis condition, then the output size would be 4 power n. But we do have the valid parenthesis condition, which is why I think then the output size would be somewhere, it can be somewhere between 2 power n to 4 power n, because the recursion tree. So this recursion tree will be, it will not be a full blown recursion tree, because we are definitely not making you know two choices at every node. And by the way, just to clarify a few things, so this would be, the height of this would be number of slots, like 2n, right? And the output size, which we just discussed, would be somewhere between, so this output size would somewhere be between, as I said earlier, somewhere between 2 power n less than output size 4 power n. So yeah, so the final conclusion is, there is a subproblem structure which we just found. So each, just to be clear, at each level, or each node will the goal is to fill a particular slot and pass on the rest of the suffix. So if you consider this as suffix, and this as prefix, sorry, and this as suffix, so their goal is to fill a part of the just one slot and pass on the rest of the suffix to the colleagues or the people, the next set of colleagues or friends. So if you see here, the other thing to notice is the subproblems keep on at each level. So if you see here, number of subproblems at the root node is just 2 power 0. It's 2 power 1, or 2. Here there's only one choice, which is why it's 2 power 1, and here there can be 2, so it's exponential, like 2 power 2, and at the end it is 2 power n. Okay, so let's try to get the pseudocode right for this solution which we just discussed. Okay, so okay, so whatever we just discussed until now is, like, we can conclude that there are subproblems. So we could approach this in terms of subproblems and come up with a recursive function which can solve those subproblems, and finally we have the solution for the overall problem. So now, some of the missing things in our solution is, so we have established that each worker node has two choices to fill the blank, right? Either open or close, right? But so let's say if but they don't have to. So even though they have two choices, since we have this valid parenthesis condition, right? So this is the key part for this problem. So how do you make sure that this condition is met in the final solution, right? So let's see if so we have established that the worker node will, so any abstract node, right, will pass on uh, so let's say this is, you can assume this as a hierarchy. So let's say this is a manager and a subordinate. So there are few things that a manager passes on to the subordinate, and that includes a part of the problem that this manager solved, which we can call it as a partial solution. Let's consider it as partial solution, and the rest of the subproblem that the subordinate has to solve. So here we don't have any string as such, so all we have is a integer given n, which is either I think which ranges from 1 to 8. So so we have to come up with a way to pass on the subproblem to the subordinate. So let's say if so 6 slots, right? So let's say this, the manager has solved one problem, one subproblem. So the rest of the remaining pairs, let's say we have the remaining, right? So you have two open and three closed, and those have to be filled in these five. So the subproblem would be, like two open and three closed, right? So this is what the manager passes on to the subordinate. So this is the partial solution, and this is the subproblem definition. So it would be, I mean, in the code, in the code we don't have to. So this should be the definition, the subproblem definition and the partial solution. So now, so how do we handle the valid parenthesis condition, right? So this is the key part of this problem. So let's say if uh, the partial solution or the prefix is, let's say, like it's, let's say prefix, so let's say if I am some node in that hierarchical chain and I am assigned this problem which I'm writing now. So let's say here prefix or partial solution in our okay, and the open for this problem will be, so I've already used, so there's like one is already used, so open would be 2 comma closed would be, closed is 1, right? So let's say if this is the subproblem, let's say if I see this subproblem and I've been asked to fill the rest of the, so this is what the prefix and I have like rest of the three slots, right? So now if I see this problem, uh, there's something like off about this problem. uh, if you see this prefix does not is not a valid parenthesis, is basically fails the valid parenthesis check. This one is also an indication that this problem there's no this problem will not have a valid parenthesis, because if you see there is open 2 and closed 1, which means the prefix already has more closed than open, which is not a valid condition for the parenthesis. So if you see, if any of the subproblem or any of the worker node sees a subproblem with this condition, then we can directly return that there is no way we could solve this problem. So this is the valid parenthesis check we need to be uh, careful to incorporate into the solution. Okay, so let's try to write the code with whatever we have understood. Okay, so let's see. Okay, so what do we need? So let's have a recurse function. So we need a prefix, we need the open, close. So let's have a result which will return all of the valid parentheses, and I'm going to declare the prefix out of the recursive function, and I will let you know what is the reason for this. So this is the partial solution, and the open and close are the subproblems. So open and close represent the subproblem definition. Okay, so what do we have? So we need a base case to for this recursive function, uh, and the base case would be once we reach the leaf node. So if once we reach the leaf node, which means our open and close both are zeros. So if open is equals to 0 and close equals to 0, then we have to append the result, append the prefix to the result. So at this point, all the slots are filled, right? So we have result dot append the prefix, right? Okay, now we have the recursive case, which is so right. So what happens, as I said, there are some scenarios where the worker node cannot have two choices, right? There can only be one choice. So let's say for the initial, uh, when we start the when for the initial manager or the manager at the root node, right, he will be having only one choice to make, right? So which means our prefix will is empty at that time. So if not prefix, which means we are trying to fill the first slot, then we only have one choice to make, which is prefix dot append. So our prefix is a list, so we only have to append the open, and now we have to recurse it, which is recurse prefix, and we have already used one open, so I'm reducing it, and the close remains the same, right? So now the another case would be, which is any abstract node, right? So we have, in that case we have open underscore greater than 0, and the other case would be if close underscore greater than 0. So what happens here? So our initial choice, so any valid parenthesis will have an open followed by a closed, right? So this condition makes sure that any worker node first choice has to be an open bracket. Next, once that is done, the next choice will be the closed one. So here is the same thing. So prefix dot append open, and we do the same thing. And we have to pop it because we are using a prefix is a list which is used overall through the recursion. And we do the same thing for the close as well. And here it would be close minus 1, because we have to decrease the close number since we are using it. Now the key valid parenthesis condition, right? So it's now why are we calling this a backtracking condition? Because this is the condition due to which we cut down the tree branches. So otherwise, without this condition, it would be a full-blown, two choices at every node. The output would be 4 power, like all the choices would be exhausted. But we don't want all the choices to be exhausted. So we are adding this backtracking condition, which we have found in our analysis, which is if the subproblem has open greater than close, then just return an empty, just return none, otherwise, yeah. So here the other thing to keep note is, since we are using this prefix as a global list, we don't want to append this prefix as it is. Like we need a copy of this prefix. Not the append or the, yeah, so we need a copy of this prefix, not the direct appending of this, because so if you do directly, then you will be getting a wrong answer. So it should be okay. So you will return uh, yeah, so let's say if this would be recurs. So for the initial problem, initial subproblem, prefix would be prefix, and n would be n comma n, like both open and close, and I will return a result. I think that should be it. Yeah, so I'm just thinking, do we need anything to be changed here? So, so do we need prefix a pop here? Hmm. Yeah, I don't think so. We need any pop here. So let's see if this works. Okay, so what is the issue? Okay, so we have defined it as close. There is one more score. Okay. So I think it should be okay. 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 So we need an else condition here, because it's either this or this. Okay. And then let's see. Okay, so we need a string, not a list. So I'll just create a string. Okay. So let's see. Okay. Okay. So I hope you understood the solution, and yeah, let me know your thoughts.